In this lecture, we will look at floor planning by integer linear programming. See, what is linear programming? This is the Wikipedia definition. It's a mathematical method for determining a way to achieve a best outcome, minimizing something or maximizing something in a mathematical model subject to some constraints. Um, so linear programming is a is an optimization technique. So often it is mentioned like this: maximize some linear function, okay, subject to some linear constraints, right? So for us it's an optimization problem where we try to minimize something, so it can be minimize or maximize some linear objective function subject to some constraints. Now, how is this related to our problem, that is floor planning? So the constraints specifying a feasible floor plan can be described as a set of mathematical equations, and then we can use commercial ILP solvers. There are commercial solvers available to solve any linear program, and this is a successful technique for floor planning, and this work was presented initially as an analytical approach to floor plan design and optimization by these authors in IEEE Transactions on CAD journal. So how do we formulate the problem? So there are a set of modules, um, and the width and the heights of the modules are known, and in the original algorithm the modules can be rigid and also flexible. The original algorithm can handle both the cases, but in our case now for this lecture we'll assume that the modules are rigid. That means their widths and the heights are fixed. So let us take the floor planning problem. We are in this space, and we have modules I and j. The lower left corner, the coordinate of the lower left corner of the module is denoted as xi comma yi, okay, and so for the module j we call it xj comma yj. And as I said, we have assumed rigid modules, so the width and the heights of the module are denoted like this: wi and hi and wj and hj. So they are constants and they are fixed, and our problem here is to, assuming a trivial case where there are only two modules, our problem is to find out this coordinate xi and yi, and xj and yj of the modules, which are variables. What is the optimum coordinates so that the entire floor plan can be minimized? Of course, the wire length is also an option, is a parameter to be minimized, but now we'll just consider the overall global bounding box of the floor plan. And of course, if you know the number of interconnections, you can do a center to center estimate to estimate the wire length. Now we look at the problem more in depth, and especially how do you write mathematically as an equation the relationship between two modules, the relative position of two modules. So we'll just take a case like this where the module I is to the left of module j. So if module I is to the left of module j, then xi, that is the lower left coordinate of the module, plus the width of this module must be xi plus the width of this module must be lesser than the lower left coordinate x coordinate of this module j, right? So this equation must be true if module I is to the left of module j. What if module I is below module j? Okay, So we can write like this: the y coordinate of this point plus the height of module I must be lesser than the y coordinate of this point. So if that is true, then module I is below module J, right? So we saw I is to the left of J, and the other case, and this third case, module I is to the right of J. So again we have the same things holding true. We can write in this way that xj plus the width of module J must be lesser than xi, right? So that I have written in other fashion because I want to have a uniformity that xi must always be on the left hand side of the inequality. So I bring xi this side, so we can say xi minus wj is greater than xj. Same equation is written in this format. This is if I is to the right of j. And the last one is if module I is above j, then again we can write that this y coordinate yj plus the height of this module must be lesser than the y coordinate of module I. So yj plus hj must be lesser than yi. Again I am writing it in this fashion to keep I on the left hand side of the inequality. So I bring yi minus hj as greater than yj. Right. So what we are doing in these slides, 4 slides, is just that the relative position of modules I and j are just captured as 4 equations, right? I being to the left of j, I being below j, I being to the right of the j, and I being above j are captured by these 4 equations. That is good. So we have these 4 equations to say the relative positions of two modules I and j, and they are governed by these equations. Now what if we have a case like this? So what is the equation relating module I and j? So we can't say that j is above I. Kind of there is a diagonal relationship. J is diagonally above I, or you can say to the northeast of I. J is to the north and to the east of I. So but even in this case we can see that the first equation is satisfied, that xi plus the width of module I is will be lesser than xj. So the first equation is satisfied. The other 3 equations are not satisfied because yi plus hi is lesser than yj is not satisfied. This would have been satisfied if j would have been further above, and similarly this and this are also not satisfied. So only the first equation is satisfied for this placement of blocks. Now what about this? For this 4 modules I, j, k and m. So you can see that the second equation is satisfied, that yi plus the height of the module I is lesser than yj. Only this equation is satisfied. What about the first equation? That won't be satisfied. The first equation is satisfied only if I is to the left of j. That is not true. The third equation will be satisfied only if I is to the right of j. That is also not true between modules I and j. And the last equation, of course, if I is above j. So only the second equation is satisfied. So what we can conclude from these two diagrams is that if two modules are placed so that they don't overlap, or for two modules not to overlap, it is enough if one of these four equations is satisfied. If one of these four equations is true, then we can be sure that the two modules don't overlap either along the x-axis or along the y-axis. Of course, I am assuming only rectangular modules. So in that case, one of those four equations is satisfied, then we can be sure that they don't overlap either along the x-axis or along the y-axis. So that is what I have said. For two modules not to overlap, it's enough if one of the four equations is satisfied. But how do you specify this in equation form? How do you specify this statement in the form of equation? To do so, we associate two binary variables xij and yij with each pair of modules. For any pair of modules I and j, two binary variables xij and yij are associated, and those modules, as I said, those variables, binary variables, they can take either 0 or 1. So obviously the binary variable pair xij comma yij can take only these four possible values: 0 0, 0 1, 1 0 and 1 1. Now we can write these four equations which we just saw in a mathematical form to make this happen. That is, to make sure that it is enough if one of the four equations is satisfied, I can write the four equations which we just saw in this format. See, what I have done is, to the original equation I have incorporated two 0 1 variables, that is binary variables xij and yij. Now what we can see from here is that for the four possible values of the xij yij pair, 0 0, 0 1, 1 0 and 1 1, one of them will be enforcing the condition and the other three will always be true. Okay, so for example, I'll just look at this example. If xij is 0 and yij is equal to 1, so we're taking the 0 1 pair. So if xij is equal to 0 and yij is equal to 1 in the above equation, what happens? So in the 0 1, what happens? xi plus wi lesser than xj plus w. This is 0 and this is 1, right? So we have this equation here. So the second equation becomes, this is 0 and this is 1, so 1 plus 1 becomes 2. It becomes xi minus wj greater than xj minus 2w. And look at the third equation now. Xij is 0, yij is 1, so it becomes 1 plus 0 minus 1, it becomes 0. It becomes just yi plus hi is lesser than yj. And what happened to the fourth equation? 0 1, so it becomes 2 minus 1 1, so it becomes yi minus hj greater than yj minus h. So look at the first equation more carefully. After putting 0 1, what happens? It's saying xi plus wi is lesser than xj plus capital W. Now capital W in this equation is the total width of the floor plan. Okay, the total possible width, or we can say the upper bound on the floor plan width, and capital H is the upper bound on the floor plan height. See, for some cases when you have a fixed outline floor planning problem, the width, the capital W and the capital H may be given. If it's not given, a good estimate of the width and the height could be this, that the capital W, the width, is the sum of the wi's, the width of the individual modules, and the capital H is sum of the hi, the heights of the individual modules. So what we are saying is that for any module I, the lower left coordinate plus the width is lesser than the capital width of the floor plan. That is the total possible width of the floor plan. That is always true. What about the second equation? Xi minus wj is greater than xj minus 2w. or in other words, you can say by bringing this side, xj plus wj is lesser than 2w. This is also true for any module I or j. The x coordinate of the lower left corner plus the width is always lesser than 2w, so it is always lesser than 2w plus xi also. Because this is true, this must also be true. Now yi plus hi is lesser than yj, you cannot say. So this is the condition actually being enforced for the 0 1 case. And the last case, of course, yi minus hj greater than yj minus h. This is always true, because if you bring it this side, it says yj plus hj is lesser than h plus yi, which is always true, because any module, the y coordinate plus the height of that module is always lesser than the total height. So if this is true, yj plus hj plus lesser than h is always true. So yj plus hj lesser than h plus yi is always true, right, as it's shown here. So what we are saying is that the fact that for any two modules it is enough if one of the four conditions is satisfied, we had actually written it in the mathematical form in this four equations by incorporating these binary variables xij and yij, and of course capital W and capital H are the total width and the height of the floor plan. So we can use capital W and capital H as the upper bounds on the floor plan width and height. Now if W and H are the upper bounds, this equation will also be true. That is, the difference between the x coordinate of the lower corner of any two modules cannot exceed the total width of the floor plan, right? Xi minus xj cannot be greater than w, it has to be lesser than w. And similarly, yi minus yj is always lesser than h. This is just ensuring that the modules are not so farther apart that they are outside the feasible boundary of the floor plan, right? This is just to ensure that they are not so spread apart going outside the feasible floor plan boundary. So the authors who have presented this paper, they have formulated the linear program in this manner. As case 1, we first take the case where the modules are rigid, that is the width and the heights are fixed. It's given in the problem, and also they have a fixed orientation, that is rotation is not allowed. So width is along the x-axis and the height is along the y-axis. Now you see, in the floor planning problem, our objective function is that the area must be minimized, and you know that area is width into height. But then if you want to formulate it as a linear program, the objective function also must be linear. So to linearize the objective function, we assume that one of the dimension of the chip of the total floor plan, the global bounding box, one of them is fixed. So we assume that the width is fixed and we try to optimize the height. We want to find out that minimum height, and in optimizing the height or minimizing the height, I'm actually minimizing the area, right? So if the width is fixed, a possible objective function is to minimize y, the height of the floor plan. So y is the variable, h is the upper bound on the floor plan height, and y is the variable which I am going to minimize. So now we can formulate the linear program in this manner, that I want to minimize y, the total height of the floor plan, subject to the following constraints: that two modules should not overlap, no two modules should overlap, and each module is enclosed within the feasible floor plan rectangle, right, of width and the capital high. So that can be ensured by this: for any module I, the x coordinate of the lower left corner plus the width must be lesser than the total width of the floor plan. Similarly, yi plus hi must be lesser than y, but this y is variable, and that all the modules are in the first quadrant, right? So this can be written like this. So we can formulate 0 1 integer linear programming. We say this because xij and yij are 0 1 variables or binary variables, and of course xi yi are integers. So I can minimize y, where y represents the height, subject to the following constraints: that these two, I said, are the constraints to make sure that they are within the feasible floor plan. So the x coordinate of the lower left corner of any module and its plus this width cannot be greater than the total width of the floor plan. It should be lesser than w, and y coordinate plus the height must be lesser than the total height of the floor plan. So these two constraints for all the modules I being from 1 to n, these two conditions must be satisfied. So these two conditions make sure that the modules are not so far apart, and the next four conditions we have already seen that these four conditions make sure that no two modules overlap for all modules I and j, okay, where n is the total number of modules. And the last condition, xi is greater than 0 and y is greater than 0, make sure that all the modules are in the first quadrant. So this is the ILP formulation for the case where the modules are rigid, the width and heights are given, and rotation is not allowed, right? So if we give it to some commercial ILP solver, you know, these are constants, the width and the heights of the modules are known, and we know W and we know capital H. And if you give it to a commercial solver and try to find out the minimum Y which will still satisfy these constraints, it can give us in no time. We also want to consider the case when the modules are rigid as before, but rotation is allowed. That is, the width can be taken along the y-axis and the height can be taken along the x-axis. That is, the module can be rotated by 90 degrees, right? So if that is the case, how that can be incorporated into the set of equations, how that freedom can be incorporated into the set of constraints. We can incorporate them very easily by associating another binary variable with each module. So let us call that variable zi. If zi is equal to 0, it means that the module I is not rotated. It is as was given in the original problem, that is, width is along the x-axis and the height is along the y-axis. If zi is 1, we say that the module I is rotated, that is, the width has become along the y-axis and the height has become along the x-axis. So the same set of equations can be modified in this manner by associating the variable zi with each variable with each module xi. So we can do it in this. The first two equations, as I said, we are minimizing the height of the floor plan subject to these constraints as before. The first two constraints, as we saw before, they just are to make sure that the modules are not outside the feasible floor plan, where the feasible floor plan is capital W into capital Y, where Y is the height of the floor plan to be minimized. So the first two constraints are to make sure that they are within the feasible floor plan. Xi plus the width for any module I must be lesser than the total width of the floor plan. So we have here, now if zi is equal to 0, as you can see here, then this becomes 0. It becomes xi plus wi is lesser than capital W. If zi is 1, then this becomes 0 So xi plus hi is less than the w, because that means that even if the module is rotated, it makes sure that it is within the feasible floor plan, right? So that is what we have done here, and the same thing holds for the height. And the next four equations, as you know, they are the non-overlap constraints. The non-overlap constraints are also modified in the same way as before. So we have just introduced a variable zi, and every time uh, there is a width, you should be able to have the width when zi becomes 0, and you should be able to have the height here when zi is 1. That is the only modification. So you can see here for this, let's just take this. If zi is equal to 0, this becomes 0, so you have xi plus wi lesser than so and so, right? That becomes the same as the previous equation, xi plus wi lesser than xj plus capital W. And if zi is 1, so we have xi plus hi. If zi is 1, we have xi plus hi lesser than xj plus m. So here, the width and the height we can replace by a common variable called m, because we have width here and height here, and sometimes the width and the height of the individual modules are interchanged because rotation is allowed. So we're going to replace w and h by a common variable called m, where m could be set to either maximum of width comma height or width plus height. So by incorporating this freedom, the number of equations actually did not change. Only the number of integer variables, the binary variables associated, has increased by n, the number of modules, because for each module we are associating another variable with that. A problem like this is best understood with an example. So let's take an example, a case like this from this book, Practical Problems in VLSI Physical Design by Sung-Kyu Lim. Here, four modules are given. We assume that the width and the heights of the modules are fixed, and let's take the case where the rotation is not allowed, that is, the orientation is fixed, the width is along the x-axis and the height is along the y-axis. So we have four modules, m1, m2, m3 and m4. So we have to formulate the set of linear equations and solve them so as to optimize this the total floor plan area. So if we have to form the set of equations, it would be something like this. So we have four modules, and we associate 8 integer variables, that is 2 variables to represent the x and y coordinate for each module. So we have x1, y1, x2, y2, x3, y3 and x4, y4 to denote the lower left corners. And we're going to have 12 binary variables. Remember, we said the pair xij and yij were for a pair of modules I and j. So here we are having 4 modules, so we're going to have 6 pairs of modules, and for each pair we are associating modules variables xij and yij in this fashion. So for modules 1 and 2 we have x12 and y12, modules 1 and 3 you have x13 and y13, and so on. So the set of linear equations are going to look something like this. So we want to minimize y. The capital y is represented as small y in this case, subject to the constraints. So first I am formulating the non-overlap constraints. As we can see here, for modules 1 and 2, these were the set of non-overlap constraints, that x1 plus the width 1, that is 4 in this case, must be lesser than x2 plus the total width of the floor plan into x12 plus y12. The total width of the floor plan in this case, you can see here, it's 4 plus 3 plus 6 plus 7, that comes to 20, and the total height of the floor plan you can calculate, that will come to 23. So that is what he has represented here. So these are essentially the non-overlap constraints for modules 1 and 2, and the same way these are the non-overlap constraints for modules 1 and 3, and you have the non-overlap constraints for modules 1 and 4, non-overlap constraints for modules 2 and 3, 2 and 4, and 3 and 4. So you can see that there are actually 6 sets of non-overlapping constraints from 4 modules. So 6 sets of constraints, and each of them having 4 equations, so that becomes 24 non-overlapping constraints. Right? Okay, now what happens then? And then of course you have this constraint that all of them are in the first quadrant, all the xy coordinates, and of course the 12 binary variables, they belong to 0, 1, and the width constraints that for all the modules, the lower left corner plus the corresponding width must be lesser than the total width of the floor plan, and the y coordinate plus the height must be lesser than the total height of the floor plan. I wanted to mention a word about the number of equations, the size of the linear program, so that you can have an idea about the time complexity of this. The first thing is that there are 2n continuous variables. You know that those are the variables for the x and y coordinates. So if you have n modules in your program, you're going to have 2n continuous variables representing the x and y coordinates. And how many integer variables you're going to have? See, for a case of 4 modules, we had 12 integer variables, right? So we have n into n minus 1, 4 into 3. So we have n into n minus 1 integer variables. And how many linear constraints you're going to have? You're going to have 2n square linear constraints. Now how do you get that number? You have to come back to this set. You can see here, if we had only 2 modules in our floor planning problem, you would have this set of 8 equations, the 2 constraints to say that those 2 modules are inside the feasible floor plan, and 4 non-overlap constraints we have got here, and of course 2 constraints to say that they are in the first quadrant. So 4 plus 2 plus 2, so you have 8 constraints for 2 modules. Remember, if you had only 2 modules, I and j, you're going to have only these 8 constraints. So for 2 modules, you're going to have 2 into 2 square linear constraints. So that's how for n modules you're going to have 2 into n square linear constraints. So this will give an idea about the size of the program. Obviously this means that as n increases, your linear program is going to become really huge, because you can see that the number of linear constraints is growing quadratically with n. And in this example from this book, Practical Problems in VLSI Design, the author has formed these linear equations and fed it to this GNU linear programming kit. So I told you that commercial solvers are available, linear programming solvers. So whatever the equations we have formulated, minimize some constraint subject to minimize some function subject to some constraints, they can be entered into this linear programming kit, and it will give you the optimum value. So when this problem which we have just seen was given to a GLPK kit, we obtain the following solution that the minimum height of the floor plan y star comes to be 12, and these are the values we got for the variables. Remember, x1 y1, x2 y2, x3 y3 and x4 y4 are all variables. We wanted to find out the optimum value for those variables such that the overall area of the floor plan is minimized. And of course, for each pair of these modules, module 1 and 2, 1 3 1 4 2 3 2 4 and 3 4, we have got these are the optimum xij yij values, and all these values have a meaning as we see here. So we can construct the floor plan from the lower left corner information. So you can see that module 1, lower left corner is 7 and 7, and then module 2 9 and 0. You can take module 3 first because the lower left corner is just the origin 0 and 0 0. And what is the size of module 3? If you remember from our thing, module 3 is 6 and 4, and that seems to be the second biggest module. Module 3 is 6 by 4 and module 4 is 7 by 7. So you can see here that it is 6 by 4 at the origin. So this, you go at the origin and is 6 by 4, and the module 4 is 7 by 7, and its coordinate is 0 comma 4. That means it's on the y-axis. So 0 comma 4, you have a 7 by 7 big module, right? And similarly, you can from this information you can construct the floor plan. So this is the floor plan solution, or the solution to the linear programming problem which we have formulated. Now any student looking at this will have the first question, that why is this space left? This could have been here. Of course, this error is happening because of an approximation we did at the objective function. You remember the objective function was to minimize the total area in a floor plan, but then we linearized it and said that we want to fix the width and we want to minimize the height. Now because of this, that is manifested as an error like this. Now in this same problem, if you allow rotation, if you give freedom for the modules to be rotated, even that problem can be solved. As it says in this example, for the same problem, if you allow rotation, you give that freedom by associating the variable zi and solve the same problem using this GPLK kit, we would get a solution like this. So obviously you can see that this is the most optimized way in which you can place these 4 modules. So although it's a simple example, when you have real problems where you have so many number of modules, you will find that this algorithm really achieves optimum solution at the cost of a large number of equations, which is one of the drawbacks of this algorithm. And this book gives a practical problem. This problem which I've just discussed is from this book. Thank you.